Lisa is playing. Can you hear?
Can't hear anything. We can only see the screen.
It is proposed to host a series of webinars. Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Hello and good day to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the Advanced Laser Material Processing webinar from the IRIS webinar series. My name is Ritu George and I'm a part of the Office of Global Engagement at IIT Madras. Joining us as the moderator today for this session is Professor Ling Soo Kong, who is a professor at the Deakin University at Melbourne, Australia. Professor Kong has a broad research interest in micro and nano fabrications and systems. His key interests include micro and nanostructured porous material, biomedical and environmental applications, microfluidics and nanofluidics, and micro and nano characterization. He has attracted more than 15 million funds from national competitive grant schemes and industry. He pioneered the design, characterization, and proof of concept development of a molecular diagnostic system that can be used for DNA and RNA detections. He has published more than 300 scientific papers with a citation of more than 10,000. He was awarded an early career researcher from ARC, that's Australian Research Council, and AAS in 2003, and Roger Seiden Memorial Fellowship from Australian Business Limited in 2002, and an Australian Award for the Endeavour Executive Awards in 2010. It is our pleasure to have you here with us today, Professor Kong. We know it's really late for you and we really appreciate you joining us today. I will hand it over to you to introduce everyone else on the panel and take it forward from here.
Thank you very much, Chairman, for your introduction. So it's my pleasure to be joining you for this wonderful opportunity. And also, I would like to extend my my thanks to Professor Samuel as well for inviting me to be part of this wonderful process. So, and also, I would like to acknowledge the two wonderful speakers tonight, Professor Josh and also Professor Chrisman, for agreeing to deliver those two wonderful relevant speeches for us. So first, I would like to introduce Professor Ghosh to deliver a talk on laser-assisted diamond brazing, the trading future. So Professor Ghosh is a professor within the Department of Mechanical Engineering within Indian IIT Madras, and he has a very extensive experience supervising quite many PhD students, and also published widely on the topic in a wide range of topics. So we first we introduce Professor Ghosh. After Professor Ghosh finishes his presentation. We will welcome Professor Christian to deliver his speech. So, Professor Kush.
Thank you, Professor Ling Zukong. It's really a pleasure to have you on this platform. And, it's a nice evening, of course, from Australian perspective. So thank you, Professor, once again. Thank you, Professor Samuel, to give me this opportunity to present my research activities in front of the global community and global fraternity of the researchers. Thank you, Professor Sivaramakrishnan, my other colleagues, and of course, the research fraternity who are present on this virtual platform across the countries. Thank you so much. Just without wasting much time, just let me get into the topic. And let me share the screen. Is it visible?
Yeah, it's fine.
Yeah. Thank you so much. So the topic I have chosen here to present before you is laser-assisted diamond brazing, the trending future. So here is microparticle you can see on the screen, which is braced on a steel substrate. I will take you on the journey of this presentation along with me, and will explain and explore the mechanisms of how the diamond can be joined and how laser can play a wonderful and exciting and future trending role in this particular regard. Since we are talking about diamond, just let me introduce the diamond in a very quick manner. Of course, the diamond is known to us as a gem material, but with engineers, whenever we deal diamonds, it's all about synthetic diamonds, because it's a synthetic diamond which we can really tailor the properties. The synthetic diamonds, it can be produced in the labs, and it can be with the repetitive physical, mechanical, optical characteristics. If you look into the process route, how these synthetic diamonds are made, there are two popular technology which are basically used for it. One is HPHT, that is high pressure, high temperature technology. The other one is CVD technology, that's chemical vapor deposition technology. We all know that how our Mother Nature produces the diamond in its mantle. So if you look into the Earth mantle, so the temperature is pretty high. That's in the tune of 900 to 1300 degrees centigrade. In that particular region, the typical element 6 gets converted to graphite under the huge pressure. So the same understanding is actually realized on the lab, not today. It's almost in the year of 1950s. But that day, it was a revolutionary exploration, and I say it's a discovery. And if you see how that is basically made in the lab, this element 6 is converted to the diamond actually under high pressure and temperature, following the same natural route. The pressure is as high as almost 40 to 50,000 times of the atmospheric pressure, and the temperature in the capsule within which this graphite is converted to diamond is about say 1500 degrees centigrade. But the production is little different, when we produce the diamond in the lab, it is actually melt in some kind of molten metal. It is dissolved into the molten metal like nickel, iron and cobalt. And then from that particular state, it is crystallized and given the form of the diamond. But when you talk about the synthetic diamonds, they're majorly into two categories. One is, the single crystals and the polycrystalline diamonds. You can see some of the examples here. These are the polycrystalline diamonds A and B, and they are all for the cutting tool applications. The C, this one also is a single crystal, single crystal CVD diamond plate, You can see the D, this is abrasive particles. Today, actually, we are going to discuss on the joining of the abrasive particle with the help of conventional as well as the laser technology. And the last one is that particular glass. It looks like a, it's a PCD, it's not glass in its true sense, but it is a PCD unit, which is used as a window in the laser processing unit, through which actually the laser passes through. Okay, because it's transparent, there is very least amount of energy which is lost to it, and diamond is a material, even over the time, it does not lose its characteristics. If you look into some of the salient characteristics, you can see the hardness of synthetic diamond. It might be a little lower than the most hard natural diamonds, in the order of 80 GPa, and for the PCDs, and for the single crystals is 80 to 120 GPa. Fracture toughness is pretty high. That is one of the reasons this synthetic diamonds are so much preferred. Being a machining specialist, I just look into this particular factor much more critically, because we are going to use these diamonds as cutting tools, maybe in the high-speed machining application, including the grinding. Of course, it has high thermal conductivity that is also required when I use the diamond as a cutting tool. Young modulus is also pretty high, within 100 GPa. So this is a very quick glance in synthetic diamonds, on synthetic diamonds, how in whatever form they are existing, whatever form they are basically exploited for the engineering purposes, etc. More specific examples pertaining to today's lecture. You can see some of the cutting tools. Here are the carbide tools, but at the tip of the carbide tools, the PCDs are basically joint. And because you don't have to use the entire things in the form of a PCD, in that case, if you really use this entire body as a PCD, then the cost involvement is pretty high. So you just need the tip to be converted with the excellent cutting capability. And on the right side, you can see several types of the abrasive tools on which the diamond particles are basically joined together. When we talk about this diamond joining, this diamond can be on a substrate joined together in different ways. Number one is very simple, ordinary chemical bonds, like a simple glues. There are a lot of extraordinary glues which can give a very good joint strength in the ambient condition. But when we use the diamond particles as a cutting tool material, and maybe the grinding tool, then the involvement of the high temperature will simply deteriorate the quality of the glue and cannot just hold the strength. So we cannot exploit the property of the diamond. So we can also sinter a diamond in the metal matrix. We can even press fit a large crystal of the diamond onto a body of the metal. We can use those kind of things in the the dressing stick, which is typically used for the grinding application to condition the grinding wheels. But apart from that, to make the abrasive wheels, like the grinding wheels, two competing technologies are there in the market. One is in electroplating, another is the brazing. Today we are going to talk about the brazing. So unless and until we know what is brazing, we would not be able to delineate much details about the assistance of the laser technology into the operation. So in electroplating, it's simple, the mechanical joining of the diamond particles to a substrate with the help of the nickel bond. The nickel is plated and it is just covering certain height. But in case of the brazing, it's absolutely a metallurgical bond. So first of all, we need to know that how we can really braze it. So for the brazing purpose, we need to understand the system, the brazing system. So we are going to braze a grit with a substrate. Usually that's a metal substrate. It can be a cermet. Cermet means it's basically composite of ceramic and metal with more proportion of the ceramic. And we have an alloy which needs to just create a bridge between the grit and the substrate. Depending on the source of the heat, you need to melt this basically alloy. And in the molten form, the alloy basically spreads on the substrate. It should react the diamond, because unless and until there is a chemical reaction initiated between the grit and the alloy, it is very difficult that you get a right strength for that. Of course, to melt this particular alloy, you need the source of the heat. So we can have resistance heating furnace. So and we can have even the gas flames. We can have the induction heating, and we can also use the high-tech technologies like laser and electron beam. We need to understand the entire understanding of the brazing should be very, very clear before we go and see how the laser can be of really a beneficial tool today to take the entire brazing technology to a new high, where the process technology is advanced, the product cost can be reduced, the cycle time can be reduced, those points. Okay, so first of all, we just focus on how this diamond is brazed to a metal substrate, which is a very essential part when you intend to make an abrasive tool, okay, which can be used for machining application, which can be even used for the dentistry, which can be used in the machining for cutting the rocks, or even can be used for grinding the ceramics. So you need to understand the brazing metallurgy very well before we choose the right heating source. So to braze the diamond to a steel, we need the typical characteristics. So what are those? Number one is the alloy needs to nicely wet on the substrate. Generally, we use a metallic filler, so metal to metal spreading is as such very easy. But as long as the weighting of this particular alloy on diamond is concerned, it's pretty critical. We need to understand the metallurgy to make it more and more efficient. There should be sound interface. When this alloy is waiting on the diamond, the interface should be flawless. Flawless in the sense it should be with minimal amount of the microstructural flaws. And these things, as if the temperature is very much involved, and you know when you join these things, say for example, I choose an alloy that gets melted at a high temperature, it reacts with the diamond, but the moment I reduce the temperature to get the filler material solidified, what will happen? That there will be differential contraction rates. So there will be residual stress. So those aspects let us just look into. So first, I will just present you in a case study, which is a very normal conventional brazing, which is industrially, the commercially exploited to a maximum possible extent. And that technology is nothing but high vacuum technology, and which requires, which most of the time utilizes the resistance heating as a source of the power to melt the filler. So here in this case study, we choose a grit, which is single crystal synthetic diamond. The alloy is a nickel chromium alloy, which is quite hard when it becomes solidified. Substrate is just a medium carbon steel, and the process is high vacuum active brazing. This high vacuum active brazing, I'm just coming to that a little more in depth. After that, we'll try to see how the laser can be beneficial. And then application is basically manufacturing of the grinding tool. So as I said, there are a lot of metallurgy involved into it. We need to see that how this filler material basically behaves when it intends to join the diamond with respect to the substrate. So it is taken in the powder form. So each globules, you can see this is basically a powder metallurgy, it is produced to the powder metallurgy route. When we melt it and we just analyze the microstructure, we can see that in the microstructure, there are nickel matrix solid solutions, some with the chromium, but in the matrix of the nickel, you can see there are some nickel silicides which gets formed. These nickel silicides actually, they has a tremendous hardness, that's 825 HP. So when the bulk hardness, if you just see that 650 or so, so the nickel silicides contribution alone is 825. Nickel is at such a much softer matrix. So this presence actually makes the material very strong, like the filler material after solidification, much more hard, as well as it's quite strong. Okay, so this is how it behaves when it solidifies. And now, if you just see after the brazing, how the diamond looks like, this nickel chromium alloy that nicely wets the diamond surface. Apparently, it's an excellent wetting, and the joint looks to be very, very sound, even after a not so high resolution scanning electron microscopy. Okay, but if we really look into the joint critically, especially at the interface, we find that there are chances of formation of micro cracks. These micro cracks generally is very, very detrimental. Okay, when we try to see what exactly is happening, we wanted to reveal the microstructure at the interface. when we reveal the microstructure, etch this portion out electrolytically, we show there is a phase which is called chromium carbide. And there is also a phase which is iron chromium carbide with a typical proportion of the atoms. But these two phases are a bit semi-coherent with the matrix. And because of that, when you solidify it, the stress level basically increases on this particular structure. And that is exactly existing at the interface. And this chromium carbide is further weighted by the nickel matrix. Now, this chromium carbide itself is ceramic in nature. Now, when we cool the entire system from the high temperature, this nickel chromium alloy I'm talking about, it has a liquidus temperature, I just need to set the brazing temperature very close to 1000 degrees centigrade to realize the brazing. So from 1000 degrees centigrade, we allow it to cool. When we allow it to cool, that basically induces the stress because the diamond contracts at a different rate, the substrate contracts at a different rate, and in between this alloy has to absorb that particular stress. And alloy is as such nickel based, so it should be supportive enough, but you have chromium carbide at the interface. This chromium is the active element into this particular alloy matrix. I didn't mention, but because there is an active element, you need to have this particular brazing realized under a very high level of vacuum. This level of vacuum is 10 to the power minus 8 to 10 to the power minus 9 atmospheric pressure. So as I said, that non-coherency and the typical very high hardness of the chromium carbide as a result of or caused by the residual stress receives a crack. That's a very nanometric opening. As such, even with this crack, the diamond can sustain a very good amount of force. So possibly that is adequate to some extent from the perspective of a grinding tool. Because when we just tested the joint strength in our laboratory, we saw that, okay, this kind of small grit, a 700 micron grain, was struck with the linear motion of a carbide rod. And we saw that it could withstand up to 81 Newton. Generally, the grinding tools do not experience this much amount of load, but this is the way the grinding takes place and the way we have conducted the experiment, there is a difference because the grinding speed is much more higher. The impact is much more, even the failure takes place at a much lower load. So what happens? This particular grain basically fails, and that fails not abruptly. It is always tending to fail at the bond level. The breakage takes place at the bond level because the residual stress is there. If you see the coefficient of thermal expansion between the diamond and the medium carbon steel, that is the substrate, there's a wide gap. And of course, the Young modulus also, there is a wide gap. So as a result, what happens when it cools, the residual stress is extreme. We try to map this, and we saw that by numerical simulation, that common understanding, which is justified. That is, the stress should be maximum at this particular bond level. And this stress is tensile in nature because it is cooling. Now, if we imagine that if there is a load which is coming from left to this side and this way, what will happen? Because of the bending, this portion will be having additional tensile stress. So which will further go, and in particular, whatever energy spent here, it will simply cross the fracture toughness of the diamond, and finally the crack will be opened up here, and then simply it will propagate to the weakest directions, and finally we basically land up into the failure like bond level truncation. So this is exactly what is happening, and this is how the brazing metallurgy basically works. We wanted to control the cooling rate, and we saw, yeah, cooling rate has also have some sort of effect. Some sort of effect in the sense, if it is very rapid cooling, then only it happens. But let me just recap the process I'm talking about. I'm not talking about the laser processing here. I'm just talking about the commercial process which is adapted to braze the diamond. That is high vacuum, high temperature. So when we cool down from a temperature which is 1000 degrees centigrade, it takes quite a lot of time in the laboratory. It takes almost 7 to 8 hours to complete one brazing cycle. Of course, because it's a radiative heating, because entire environment inside the hot zone, it is under vacuum. So only the mode of heat transfer is the radiation. So but still we can control the cooling rate, because you can suddenly switch off the heat input to the furnace, or you can still allow the heat input to be there to some extent, so that cooling rate can be controlled. Of course, we have seen that the cooling rate also has a tremendous effect. If the cooling rate is high, the stress level also will go high, which is not good. So we thought that how to tackle this problem metallurgically, first of all. And this metallurgically, as I said, the root cause is the residual stress. We thought that why not to use a filler alloy, which is much softer in the sense it is much more ductile in nature, okay, and with adequate young modulus, and that means basically it will absorb. It is more tough. Okay, we need it tougher, but at the same time it should be able to absorb. It should show more ductility. That means the strain at fracture that should be much higher than the nickel chromium alloy. And when we just used a silver-based active alloy with the presence of titanium as an active element, so we saw that there is absolutely no crack at the interface. So this major problem, which is industrially found, it could be just resolved. Now there is another issue. I just must share with you. See, we are using a silver-based alloy, and this silver-based alloy is quite sharp. That is why it can withstand that stress, and it is not allowing any crack to initiate. Of course, here is also an active element like titanium. Titanium is also reacting with the diamond, making titanium carbide at the interface. Okay, that is also almost ceramic in nature, but still, since this the silver copper matrix is much more softer around it, it gives a much more cushion. I'm just talking much more in a less scientific terminology, cushioning. But finally, what happens, main thing is basically the absorption of the residual stress is much more efficient. Okay, so we can get rid of this crack problem, and then we thought that why we should actually modify this alloy a little further. So we wanted to reinforce this alloy with some ceramic component, both micro and nano, and we wanted to see that, okay, let this alloy be little more wear resistant, because it is too sharp. And this grinding tools, if it is used to grind, say, ceramics, or it is used for grinding the rocks, those debris, or we say the grinding swaps, they will simply abrade. The grit will not get broken, but the alloy will be worn out, and the grit will be prematurely pulled out from the matrix. That we didn't want, so we wanted to enhance the wear resistance characteristics of this alloy, and we just added some ceramic reinforcement, and we did it. So this is all about joining. But then after the joining, how really we how do we place the diamond particles? Because many cutting tools needs a proper placement of the abrasive particles. So this is one tool which we call as a diamond dresser, which is used to condition the grinding wheels. Now, the same thing if we use for grinding something else, or maybe we manufacture a wheel where there is a cluster of the grits, rather instead of the grits being placed like an uniform distribution manner here. So what will happen? That the intergrid pockets will be basically clogged with the debris, and the functionality of the diamond cannot be realized, and there will be a failure of the tool because of that. So we need to place the grit. So this placing of the grits, we need to develop certain technology through which you can plant these abrasive grits on the filler alloy. So basically we paint the top surface, the active area, and then with the help of a very state-of-the-art technology, which is also developed and patented by us, we just pick the particles and just drop it, and then create a typical array, and then we allow it to braze. Well, why I'm telling all these things, because if we understand the manufacturing perspective, we can really make out how the laser can be extremely beneficial if we just come out of this conventional mode. So this is how these dressers are tested. The grinding wheel is rotating. The dresser is mounted on a dynamometer, which measures the force. and then we allow it to brace the grinding wheel at different conditions. And then we see that if the diamond grids are dislodged or not. In a similar fashion, we also made small grinding wheels, which are used for internal grinding purposes. And you can see here, the small diamond particles are braced and in a very nicely ordered manner. This technology we are talking about, this has been developed here and we have patented. So we peak and grid, just peak and drop the grids in the respective location. And in that way, we manufacture the entire tool. So we need to first have a paint, and on that you need to plant the grids, and then you have to go for the brazing. We are talking about active brazing. We are talking about active brazing with a filler and to be realized under a very high vacuum. And the entire process technology, since it is happening under the vacuum, it is actually very much time consuming. Second product is a small grinding wheel, as I was talking about. You can see the grids are nicely placed here. Not only that, this technology enables operator or a manufacturer to place the grids with all uniform heights. That is the advantage of the active brazing and the technology we have developed here. And when we test such kind of tools during the grinding, we have seen, yes, the strength is pretty good. If we replace the nickel chromium, that hard filler alloy, by a softer matrix like silver, the tool life is quite few folds. And these tools are also supposed to rotate at high RPM. And that is, this technology is also quite capable of withstanding all those issues related to the high-speed grinding. Now, as I said, that we just compared the performance of nickel chromium, silver copper titanium, and the additional matrix. This is a patented composition, so we didn't disclose much details. So we can see the results, how many number of grids are getting broken here. The grids never get pulled out because pulling of the grids takes place when there is a weak interface. But grid breakage takes place, that is because the defect of the grids defects inside the grid, and of course the process residual stress. Okay, but we use silver copper based things, we can reduce this kind of failure to a greater extent. We use the ceramic matrix, the similar order of failure can be maintained, but we get a bond which is much more durable in nature. Okay, so this is all about the conventional, and not only that, we also try to make a very large diamond wheel, and we want it to grind. And normally the grinding is done just with 30-40 micron depth of cut. We have seen our technology of making the wheel is making it capable to withstand even a depth of cut in the order of 1 millimeter, and that be it is machining aluminum composite. It's generally aluminum machining is done by the diamond coated tools, but you can even grind the aluminum if you can make the tools in this particular with the help of this technology. I'm talking about technology not just from the brazing perspective, also the planting of the grids in an uniform manner in an ordered array. This ordered array is according to the design's requirement, what exactly it is going to do during the grinding, how it is going to interact with these things, how the chips will look like, what should be the parameter of the grid spacing so that the clogging of the chips, or we can say the loading of the wheel can be completely avoided, and we could successfully do that. But the bottleneck here, we should talk about two things. One is that it's a high temperature process. So although it is 1000 degrees centigrade under vacuum, but still we saw that it is prone to the graphitization. That is number one. Number two, we are using, as I said, again, I'm repeating that thing. We are just doing this brazing operation under a vacuum furnace. So from 1000 to that ambient condition, it takes a huge amount of time to come here, come to that ambient condition. So altogether, a brazing cycle, if it starts in the morning, it is just unloaded in the evening. So it's not at all very productive from that particular perspective. Can you not do it very fast? And possibly in that regard, laser technology can do the wonder, and it can show us some direction. So people started working on the laser technology, and they wanted to use this lasing operation and to see that if the diamond can be brazed very successfully. So the question basically arose in the mind of the researcher: can it not be taken to a new high with the help of the laser brazing technology. The immediate advantage with the laser brazing technology, you can just see just a quick glimpse on a video. This is, I don't know whether it will operate, why it is not working. Yeah. So this is a commercial video. There is no commercial intent, just to show that the lasing process is so fast. It can be so sophisticated today, and it can be nicely automated. So it's absolutely robotic control. So this is the two plates of automobile roof. Basically, this is typically, automobile roofs are basically, this kind of laser brazing is basically carried out, and here it is just a industrial prototype to do the things. And here you can see that you can have the use of the multi-point laser. Actually, there is a it's a trifocal lasing operation. You have two frontal laser beam, which will simply try to preheat the sample. And number two, this particular plate, which is being brazed here, it is actually zinc coated. So you need to ablate the zinc. So those two things are just used to ablate the zinc. And then the mother or the primary laser, which is at the center, that is used for the melting the filler alloy. Okay. So that is how it happens. I wanted to show these things because just to give a feeling that how fast the process is, and how sophisticated it can be, and it is a brazing. So can it not be extended for the diamond brazing too? So the immediate advantages I just tried to note. No bulk heating. It's a very localized heating. You just imagine if we do the things under the high vacuum, the entire things by the resistance heating, there's a hot zone. And that is basically heated up. That is heated up with the help of the radiation heating. And so whatever things are there, there will be bulk heating. So lots of energy will be spent out for that. So here in this lasing operation, we have low heat input, low power consumption, localized heat, and you can have a precise control of the operating parameters like laser peak power, intensity, fluence, pulse width, pulse frequency, and above all, you have the operation flexibility and the scope of automation, which altogether makes the things very, very fast. Our major objective, can we not make the things very fast? Yes, the research community initiated the things in the last 10 years. Some works have been going on, and this is just a couple of case studies I will just present in sequence. Here, it has been attempted like a 300 to 400 micron crystal was based on a 45C45 steel, same nickel chromium alloy what we are using for the furnace brazing. Yeah, the temperature of the brazing is 130 degrees centigrade, and here it is a CO2 continuous wave laser was used. And finally, it has been observed that there is no crack. There is, in spite of the things that the nickel chromium alloy is used, and weighting is pretty good. The same metallurgical reaction, because the chromium as an active element, it makes the chromium carbide at the interface and makes the appreciable weighting to take place. But some of the salient observations, they show that the laser fluence, basically it is a specific energy. So you have the laser peak power, you have the laser power into that multiplied by the that pulse width divided by the beam area. So it has been observed that there is a critical value, and that particular critical value, when it crosses, only the problem comes. Like if it is above 253 joule per centimeter square, the graphitization takes place. And even little more than that, the diamond cracking takes place. But anything beyond this, there is a range they found, 240 to 253. So there is no sign of graphitization, as well as the melting and all those weighting is very proper. So there was another case study which was there with the same alloy. This is with the fiber laser, and same kind of solar material, nickel chromium. And so obviously the chemistry of the joining is the same, what I expected or what we explained during the brazing of the things under the high vacuum and resistance heating technology. Now here you can see that this is just they wanted to they just wanted to make a cluster of diamond along certain width, and this is just to changing the speed. So the scanning speed also matters a lot, because depending on the scanning speed, the specific energy changes. That means the energy concentrated on a particular area that changes. And when we increase the speed, we have seen that if it is very low, it is detrimental. And the community it has been done by W. Long in 2020, quite recent paper. So they have seen that this speed, if it is something in the tune of 3 to 4 millimeter per second, okay, that is good for the quality of the diamond brazing. Okay, so and this entire environment, one more thing I must tell, this is not being done under the vacuum. This can be simply carried out under the argon atmosphere. Of course, the vacuum brazing, what we talked about, that also can be done under the argon atmosphere, but no, that has some extra hazards, because although we use a very high quality of the argon, the problem is that the time involved into the entire process is pretty long, and here the time involved into the brazing is pretty short. That basically does not allow the diamond to degrade much chemically. So here again, as it is quite understandable with the common logic also, the lower the speed, the laser will be exposed to the diamond for a long time. And the major disadvantage in this laser technology here in this particular approach is when we approach the interface, it is through the diamond, of course. So it is the diamond, it is not that just the root can be exposed for the heating. Of course, you can have a temperature gradient, but that is very, very difficult. So there is difference in the color the group has observed. So if you increase the speed and if you have a very low speed of scanning, so there is a change in the color. So this change in the color is nothing but because of this graphitization, the order of graphitization of the diamond. So if it is very fast, then the graphitization takes place very less. So the black diamond grades, it would be much more lesser in the percentage. So they just say, if you just have a look, so on any track, there are n number of diamond particles. So this is just counted how many numbers of diamonds were just yellow, how many are brown, how many are black. And it has been observed that the black diamond grades, number of black diamond grades are pretty less in case of the high speed. And that is because of the graphitization can be completely avoided. The red one is indicating the only the presence of the pure diamond. The other one is just presenting the presence of the diamond as well as the graphite. So a salient observation from this as noted, 3 millimeter per second and 73 joule per millimeter square specific energy. That is good. Graphitization could not be avoided. It was more or less present in all cases. So width, it can be, of course, controlled. That also can be controlled by the scanning speed. There is another study. In this case, it was the diamond was joined with an aluminium. So many grinding tools, we observed that if they're made of the modern day aluminum alloys, they're pretty advanced, and they can really sustain the grinding loads and all those things which are involved into this. And the 7075, it is even used for making the resin bonded wheels. So I think the group decided perhaps that why not to attempt this particular alloy for that brazing of the diamond. And in this particular case, they use the fiber laser of 500 watt, but of course, utility of the power is just restricted to 140 watt. And so scanning speed is 20 millimeter per minute, spot diameter is 1.5, again an argon environment. So they saw that yes, the brazing could be done successfully. And if you see that diamond here, the diamond is nicely brazed with the filler. There is it's a good weighting. And ultimately the alloy is also fused with the aluminium nicely. So almost it is unwelding on the, so it's a hybrid joining, you can say. The brazing is taking place between the diamond and the alloy, filler alloy. And between the filler alloy and this is almost like in welding aluminium, because the melting point is above the melting point of the substrate. Melting point of the filler is above the melting point of the substrate. So this is even we can manufacture the research group has presented that some of the tools they manufactured through this, and they've observed that joint strength is pretty good, and but the failure mode is majorly the pull out. There is no as such breakage of the diamond. So these are the few points, few result which indicates that the fastness of the process of the laser can be utilized much more productively for making such kind of tools. This is again a CO2 laser which is used just to see the effect of the different wattage And again, it has done in the argon atmosphere. And it has been observed that, that the grids are quite abrasive particles are retained on the substrate matrix. And the reaction products in the interface is same, like if it is titanium carbide, it's little discontinuous layer, which is good for reduction of the residual stress. But at the end of the day, when the joint strength was tested, it was observed it is adequate for the purpose it is made for. So this is a couple of things. But here, as I like to mention, that the laser is basically focused to the top, and most of the time the diamond is exposed, and it has to, because the laser is passing through it, and because of that, there would be sometimes cracking on the diamond, and what is happening is the graphitization is also taking place. Okay, so this attempt was another attempt where the group wanted to introduce the diamond through a nozzle, so from a side direction, so that laser will not interact with it for long time, within that small millisecond time span I'm talking about. So all these attempts, whatever has been made, super, they're reporting about the pulse width is just a millisecond. Okay, so whenever they are using the pulse. Okay, otherwise the scan speed is also should be such that the irradiation time on a particular grid is well controlled. It may not be in that case in millisecond, but it would be on the order of few 10 seconds, maybe 10-20 seconds. There is another work actually. So this work actually also noted, there is a diamond crack, and just 1 second, additionally, what this group did is that they tried to introduce an ultrasonic agitation onto the substrate. So this ultrasonic vibration, if it is introduced to the substrate, they have seen the mixing of the alloy with the intermetallics it is getting formed, that is much more uniform. And they saw that the interfacial layer, the interfacial reaction layer, if it is a silver-based alloy, it is a copper tin alloy here that people used. So that was all tin, titanium, intermetallics, or finally the titanium carbide. Their mixing is much more. The titanium carbide interlayer was much more smooth, and the intermetallics formed were much more finer in the matrix. So that is the way it is happening, and it is nicely done. And if it is assisted by the ultrasonic vibration, it has been observed that the weighting is much more improved, and whatever possibility of the crack, that can be eliminated even much more efficiently. So this is in brief about the laser brazing, how it is doing. So now let me just try to summarize the takeaway points. So if I just adopt the laser assistance in the brazing, so in the very first place, the immediate benefit which comes to me is the rapidity of the process. The production cycle times, instead of few hours, it is few seconds, or maybe for a tool, it is just a few, just 10 to 20 minutes, depending, of course, depending on the size and shape of the things. The small wheels, whatever I've demonstrated you, which is manufactured in our lab, that can be just made in 10 minutes. Not only that, since we are trying to plan the grids in a coordinate controlled manner, equispaced, in a very nicely arrayed manner, according to a custom design. So this can be done perhaps by the laser much more efficiently. Nobody has done yet, but the scope is wide open. But the bottlenecks, of course, that has been noted, since the interaction is there with a very high amount of the peak power, the temperature, localized temperature goes up much more than whatever is required. That is how the researchers so far are reporting. But perhaps we need to control that one, and that can be controlled much more efficiently if we replace a continuous wave laser by nanosecond or other femtosecond pulse laser, by controlling the peak power, the pulse width, the pulse frequency. Okay, and if we can really do that thing, we would be able to avoid the whatever graphitization it is taking place, and of course the interface and all those things can be made much more smoother, uniform, and much more stronger. That is the takeaway points from the reported literature so far. But what I like to conclude that the way ahead is much more glorious, but we're just walking the path. And I think the next 5 years, perhaps it would be the laser technology, which will simply, add quite a lot of value to the commercial market for manufacturing the abrasive tools. Okay, this is another study. Again, it is just to play with the frequency and the pulse width, and people have seen that, yeah, if overall energy per unit area is controlled, then the diamond can be better protected. So this is again just to play with the frequency, pulse width, and the wattage. So there is some other applications also, the laser we can use to make the abrasive tools. We are talking about the abrasive tools here. So you perhaps know that there is a rigid bonded tool, rigid bonded wheel, which surface can be textured in a very nicer manner with the help of the laser, very fast, very efficiently. And this kind of texturing is very necessary because the wheel during the grinding, it has to accommodate the chips. Not only that, it has to make the cutting fluids very effectively working. Otherwise, in grinding, because of the very intimate contact, the efficiency of the efficacy of the grinding fluid is not always properly realized. This is another form, which is a different way of making an abrasive tool. Here is a micro tool. Micro tool, like, if I just want to have just a 1 millimeter pin, and on that I want to brace the diamonds, it's quite challenging because the diamond crystals are, it would be few 10, 20 micron, particles, and even those particles need to be joined, and it becomes a little critical and tricky to realize a successful joint. So a group of researchers, they just took a very innovative approach. They just coat the entire substrate with a CVD diamond. Okay, the CVD, through the CVD, we can build single crystal, we can build a polycrystal also, but this is a single crystal. And then that particular layer is basically textured in such a way that each textured part becomes like a grit, an abrasive particle. And in addition to the common understanding that, okay, now they have opened cutting edges, but they can be made with uniform geometries, which is actually the disadvantage in case of a grinding. We don't have a control on the grid geometry, but here every segment can have a uniform geometry so that the grinding performance can be very much predictable and your product quality will be much more predictable. So this is how the laser technology is assisting us to make the diamond tools. I think with that, I just want to conclude. I think my time is, perhaps I've overshot a little bit. Yeah, so this is in gross, in a summary, like bottom lines, the process is evolving. Scientific understanding for high quality joint is not yet understood well. Unless and until we do that, really we cannot make it realized in the form of a successful product. No report so far as research by us found reporting a commercial application yet. So there's a huge amount of scope lying in front of us. So, and it has a tremendous future considering its low power consumption. And of course, because of the main thing, that is, it's a very fast process. It can reduce the production cycle time to a very appreciable extent so that we get a commercial benefit of it. With that, I thank you. Thank you, audience. If you have any question, you may please ask.
So thank you, Professor Ghosh, for a wonderful presentation. I think that's what the first comment presented from the audience. He said it's an incredible presentation. I can't agree more on that. So probably before I ask questions on behalf of our audience, I would like to first to say, today, actually, before I joined the webinar, I thought we have you and also Professor Krishna from two different backgrounds. One, because I'm an engineer as well, we could be more say we are engineers, and Professor Krishna could be a scientist. So, however, after I hear from your presentation, it seems you are an artist as well. So when you present making such very, very fine microstructure, very fine materials. Also, it's just like art. So I really like to first congratulations to you on doing such wonderful research. So we do have a couple of questions from our audiences. So the first one was, in the case of laser-assisted breathing, what are possible areas where haze will be formed, and what will be its effect on the strength of the tool?
Yeah, so I think is it on haze, like heat affected zone? I didn't.
Yeah, that's what they say.
So in this particular brazing, say the filler material is like a standalone member. Like we are not melting the diamond, we are not melting the substrate. So filler material is itself is it melts and then it reacts, or I can say during the process of the reaction there is a diffusion and we get the bond very strong. So as such. So this particular is very much unlikely to be compared with the welding operation where the haze is very much predominant. And but effect of the, if you say heat affected zone, so all the microstructural changes which is there, which is only there within the filler alloy and the reaction layer. Okay, so that is there, but the microstructural forms, whatever changes is taking place. Yeah, that is appreciable and that is acceptable from strength perspective. Lot of intermetallics form, and of course when we talk about the laser brazing, so it's an instantaneous cooling, almost it is very quick cooling. So due to the quick cooling, it is expected that the grain structure would be much more finer. That has been also observed. But as such, so-called traditional haze is not there. But if we take an substrate like aluminium, yes, there is an haze, and in that haze there is a potential issues because we can see the aluminium is melted and getting solidified, and there is a columnar structure. At the center, there is a chances of some kind of porosity. Of course, if you control the frequency and if you control the peak power, this haze effect, the detrimental effect of the haze can be minimized to a very great extent.
Okay, thank you for your wonderful answer. So another question now was, can I use it in titanium 5553 alloy?
I'm sorry, I could not get.
So used for another material, for toy titanium 5553. So you use different substrate. So the audience just would like to ask you whether we could use your technology for another substrate.
Okay. So do you mean that if we change the substrate, what happens?
Yes, probably, yeah.
Right, yeah. So here, see, this thing, we are making the abrasive tools. So our focus is on the steel majorly, the medium carbon steel to low carbon steels. We do not use a very high strength, low alloy steels, that kind of things. Because we want to have the substrate also as much as ductile as possible. So whenever we use titanium and all those things, yes, that can be also done because we are using an active filler here.
Yeah.
So the moment we have an active filler and we have silver, copper, and along with the titanium, hafnium, and zirconium, so that we can just control the proportions, and that is possible. We can also use a titanium as a substrate.
Okay, thank you very much. So I would like to suggest we probably stop here first, and then after Professor Chrisman presentation, we could have a panel discussion, and then invite some further questions to both of you. So thank you very much, Professor Gershon, for your wonderful presentation.
Thanks, Professor. Thanks, Professor Lynch.
Yeah, thank you. So now I would like to invite Professor Chrisman to give a presentation. Professor Chrisman is a professor within the Department of Physics. So I know I work with non-marriages. So that's what we are here. We have science, we have engineers. So today it's a wonderful marriage between science and engineer. So now we will pass on to Professor Krishnan for some wonderful, probably more fundamental research from your side.
Yeah, thank you, Professor Kong. Am I audible fine?
Yeah, fine.
Great.
Please.
Okay. Thank you so much for the kind words of introduction. Indeed, a multi-dimensional institution like the Indian Institute of Technology, Madras, indeed is a place where these borders and boundaries between physics and technology often tend to melt away and give way to more organic and collaborative research. And it's indeed a pleasure to do this at IITM. And I would like to thank Professor Samuel and the Office for the Institute of Excellence scheme for giving me this opportunity and organizing this wonderful evening that is dedicated to exploring the interaction between laser pulses or lasers and materials. And my task this evening is to really give a focused view as well as present some of our work as representative elements on femtosecond laser pulses, which I claim are the cutting edge of are at the cutting edge of laser materials processing. So I'm housed in the Department of Physics here at IITM, but I indeed work extensively with several colleagues through the CALM Center, which is hosting this event, and also with work groups along similar lines of laser matter interaction in the Quantum Center for Diamond and Emergent Materials, as well as the group on micro, nano, and biofluidics. As the introduction said, we launched these work groups this year towards becoming centers of excellence in the near future. And I'm also glad to coordinate and extend the services of the femtoscience facility of IIT Madras, which is about 6 years old now. So indeed, it is my immense privilege and pleasure to both acknowledge and showcase the extensive collaborations which I have, especially within the Indian Institute of Technology Madras, IIT Madras, in the Department of Engineering Design with Professor Nilesh Vasa, in electrical engineering with Balaji Srinivasan and Anil Prabhakar. And as you can see, I've extensively collaborated with the mechanical engineering colleagues, names beginning with A, Arun, Arunachalam, Ashish, all the way going down to S and V. So Professor Satyan, Professor Pallab, Professor Samuel here, Professor Ramesh Babu, Professor Vijay Raghavan, Professor Shanmugam, and my late dear colleague, Professor Saundra Pandian. And my office is also in the mechanical engineering block. So in that sense, I guess I'm a physicist in disguise. Of course, I work with colleagues in the physics department, Ramachandra Rao, Basudev Roy, Vidya Praveen, and others as well, but I've quoted those with whom I particularly work on laser matter interaction. It was a pleasure to collaborate with Dr. Errol Marl, who is now a faculty at an engineering institution nearby, a few hundred kilometers from south of Chennai, and with Professor Preeta Nair at SSN University, and more recently with Dr. Sunil Magadam at the Center for Machine Tools in Bangalore. We've been generously funded by the Department of Science and Technology, the Ministry of Education explicitly, which also is the parent ministry which funds IIT Madras as a whole, and we've got particular institutional funds. And we have collaborated with industry colleagues, India Pistons Limited, all of these iconic companies, either entirely private or public-private partnerships, Indian Oil, then Carborundum International, QME, Mahindra, and Ashok Leyland, who are automotive manufacturers. All of these people have, as we will try and convince you during this talk, a lot of relevance to the work that is going to be showcased in this presentation. Of course, Professor Kong, please do alert me on the time whenever it is probably about 5 minutes or 10 minutes left for me to conclude. I have a few slides on a couple of different topics, and I will attempt to cover them in a broad sense so as to give this wide variety of audience a sense of what we are doing and what this science is all about. In my talk, the outline of this presentation itself is to motivate why, among other things, or we would like to use femtosecond pulses for materials processing, which involves a wide variety of things, but I will focus on micro and nano structuring of various kinds, both ablative structuring as well as in a sense non-ablative, which is modifying refractive indices or surface properties for that matter. Some of this may also resonate with Professor Kong's own expertise, who is again very kindly agreed to chair this session so late in the evening from Australia. In a sense, I will give a bird's eye view of the physics underlying the femtosecond laser matter interaction, what is unique, what is different, and why we should really use this. Although I will not really have showcase test cases to showcase the work on laser welding, which my colleague Professor Ghosh earlier elaborated so wonderfully. Femtosecond pulses are also very good for welding, especially on the micro and sub-micro scales. And in the second half of the talk, I will showcase representative work with colleagues in the CALM group, that is CALM group, MNBF group, and also the QC DEM group, and maybe also indicate some directions for the future. So what indeed is the motivation for femtosecond laser microstructuring and motivation for applying femtosecond pulses to this area of work? The one of the key reasons, or maybe the reason, is precision. Of course, machining is synonymous with precision and probably even control, but mechanical engineers of course know this best. But I pick on this very important word, that is precision, and I hope to convince you that femtosecond pulses are ideally suited for this. And for many other applications, probably they are not as well suited, but then there are very well suited lasers on the broad template that we have. One of the key advantages of femtosecond laser pulses is that they provide almost a single platform to work with soft and hard materials. This, if one thinks about it, is somewhat unique. Probably not every tool is very well suited to interact and do things or modify soft materials as well as hard materials without actually a significant change to the platform itself. But femtosecond laser pulses can indeed play the role of a one-stop solution for soft materials such as polymers, plastics, polymers of various kinds, and so on, as well as, and it has been demonstrated, are ideally suited for microstructuring on really hard materials like diamond and really important materials such as semiconductors and others. And to give it a local context, the reason why we undertake extensive work here, both, together with Professor Samuel's lab, I would say, who have now also installed a very nice micro machining system with femto and picosecond pulses, is to rejoin the national initiatives on making things in India, which is essentially a call for indigenous manufacturing and a call for indigenous entrepreneurship through the Startup India schemes. So, well, yes. So why use femtosecond pulses for materials processing or structuring? Essentially because, like all laser tools, primarily it is non-contact. It's a very flexible tool, as I will hope to showcase. In many cases, it even plays the role of a single step and sometimes even a single pulse or single shot tool. And it brings in very unusual degrees of precision, especially for laser-based techniques. So in one nutshell, I'm flashing here the associated importance of femtosecond or ultra short laser pulses. One of the things which was also alluded to at the end of the previous talk by Professor Ghosh is the heat affected zone, which is essentially the extent to which collateral damage occurs when we ablate or process materials with lasers. In the case of femtosecond pulses, it has been claimed, and very rightly so, that this process is essentially very athermal and consequently rather cold, synonymously perhaps, and that when you use femtosecond pulses for processing materials, things like microcracks and extensive debris formation or formation of recast layers is minimal and can even be reduced to negligible extents. Now, these two charts here on the right are very interrelated, and I'm going to dwell upon them a little bit in detail. The outcome or the effect that is very desirable in our case is this very popular view graph, which we have sourced from this web page, but several uh, laser companies and laser micromachining manufacturers like to showcase this on their website. Essentially, on the left is a typical nanosecond or a continuous or long pulse laser beam interacting with a surface and subsurface volumes in a typical material. Let's say this is a hard substrate like silicon, diamond, or whatever. One could also think of, say, soft materials like polymers. And on the right half of the view graph is ultra short or femtosecond, or I would rather call them sub-picosecond and few picosecond pulses interacting with the same material. Now, this view graph or cartoon essentially shows that a whole lot of heat affected damage or thermal damage occurs in the case of long laser pulses. This is essentially because of the fact that apart from every other thing, these pulses tend to heat the local volume a lot and tend to start melting the system, which is not always what we want. If I want to remove material, I would really want to ablate or remove extrude material from a certain voxel, that is a voluminar pixel, a three-dimensional pixel if you wish. But this is not really something that long pulse lasers do alone. They also damage it in the sense they melt and so on. I'll show you some view graphs so that where this becomes extremely evident. And on the right hand side, we have femtosecond pulses. These, owing to the way in which they interact with matter, they essentially achieve this knife through butter type of interaction, right? There is almost no cracking, hardly any melting. Well, there is, if you control the conditions well, there is almost no shock wave and very little or minimal or no heat transfer. In fact, one could, in transparent materials, even do subsurface material modification without damaging the top surface at all. The reason, and the very important reason why these two are different, is because femtosecond pulses predominantly generate a plasma, which is a soup of electrons and ions, to put it very crudely. But then ionization is the primary mechanism with which these ultra short femtosecond or picosecond pulses interact and extrude materials. And this, of course, is something that is exclusive to femtosecond pulses, because the typical band gap of many of these materials is exceeds the energy of a single near infrared or an optical photon, and therefore you need to invoke nonlinear processes in order to ionize the material, which femtosecond pulses do very well. And why they do very well, why they do the ionization very well, is something I will try and convince you through a few back of the envelope numbers. But this stark difference, one being a largely thermal process, another being a largely athermal process, is essentially consequent or due to the fact that the time duration that a laser pulse interacts with matter is indeed very important to the way in which energy transfer takes place between the light field, radiation field, or electromagnetic wave, whatever we like to call it, and the medium. Okay, so on very short time scales, a femtosecond is 10 to the minus 15 seconds, a picosecond is 10 to the minus 12, and a nanosecond is 10 to the minus 9 seconds. On very short time scales, energy is absorbed, and on sub-picosecond time scales, the energy really remains with the motion of electrons. So one can really think of this as electrons getting excited by this. On picosecond time scales, the lattice, that is the atoms themselves, start to move. Of course, if they have to move, we have to give them some energy, right? That's essential Newton's laws even taking place, although these are quantum mechanical systems. But then on picosecond time scales, we tend to push atoms. On longer time scales, heat diffusion tends to take place from the region where the heat source is placed onto extensively larger volumes. Now, if I use very short laser pulses, then Predominantly, these pulses interact only with what we may call the electronic degrees of freedom, or they talk to the electrons and maybe to some extent to the lattice, but certainly they don't start breaking down or heating up the system extensively. This is a very cartoonish but fairly accurate way of describing why heat affected zones and femtosecond laser pulses are indeed interacting with matter in a rather cold or athermal way. The much more underlying, you can say, physics also has to do with the nature of plasma that is formed here, which I will not elaborate extensively in this talk, but rather showcase the consequences of this unique form of interaction that these pulses have when they engage with materials as against all other forms of laser pulses or continuous wave lasers. Now, in the rest of this talk, if you're still not convinced that these advantages exist, through our own work that is done in this lab together with several collaborators whom I have the pleasure of working with and I cited earlier, we use these facilities available here, the femtosecond laser system, a micro machining end station, and I actually work, as Professor Kong sort of guessed, on the physics of laser matter interaction, which is a physics oriented study. This is the system that we use for that. It's an ultra high vacuum system, entirely home built with a time of flight mass spectrometer to study ions and also electrons, which are emitted from these the laser matter interaction scenarios. But I'm not going to go into those aspects or our research thereof in this talk, owing to limitations of time. But this is something that we can discuss maybe at the end or even converse through emails. Now, a few numbers which would hopefully try and convince us that these lasers are ideally suited for the kind of work that we are going to showcase here. This black box right at the behind is the laser system. It is an Astrella laser from Coherent, an American laser vendor. This is a typical titanium sapphire femtosecond laser with the shortest pulses being 35 femtoseconds, but we tend to use longer pulses as such. Each of these pulses can have a maximum energy of 6 millijoules. It sounds rather small, but I'll hopefully convince you that this is more than sufficient. These pulses are fired repetitively in a time series with a repetition rate of 1 kilohertz. This is fixed in the case of this laser, giving an average power of 6 watts, that is 6 joules per second. And we typically focus these down to best spot sizes of about 5 micrometers, which may be a slightly sort of on the lower side. Realistic could be like 10 micrometers, but that depends upon the focusing element or the microscope objective which we use. The peak power, which is essentially the energy per unit time and the maximum of the energy per unit time here, although each laser pulse seems quite delicate, just 6 millijoules, because of the fact that these are sub 100 femtosecond pulses, it is huge. We have about 60 gigawatts of peak power in every laser pulse. Of course, this is only the peak, but even this has a lot of significance. Why? Because we can focus this down to small spot sizes, and intensity, which is essentially the power per unit area incident on any sample, can be varied very nicely between about 10 to the 10 to 10 to the 16 watts per square centimeter. Now, what's so special about these numbers? 10 to the 16 watts per square centimeter is typically the electric field experienced by an electron, which is bound in an atom, or in a crude cartoon model, which goes around the nucleus in an atom. It is bound by the electric field of the nucleus, right? This is something we learned in school. Now, the applied external electric field from this laser can challenge the native Coulomb potential, right? So in that sense, the interaction, therefore, is very, very nonlinear between the laser and the material here, which actually underlies these tremendous advantages that I spoke to you about. Plasma formation, and hence a different way of ablation, which leads to a very athermal and precise process. Okay, so these numbers in one sense are quite important to be maintained in order to get the best results. We also do spectroscopy of these materials in our lab. We can tune the laser wavelength using an optical parametric amplifier, and we have an automated transient absorption spectrometer, which can measure absorption spectra as a function of time. So we can indeed go beyond just processing materials and study them in great detail, which we also do. Okay, now coming down to the specifics of laser matter interaction and micro machining in our lab and in our work group. Essentially, this is the gantry, a granite gantry, and the path of the laser beam going from the top left to the right towards the center of this setup and then going down is shown. And this train of laser pulses is focused onto a substrate using a microscope objective. And essentially what is then done is that the laser beam is held fixed in space, whereas the sample which is placed on these XYZ three-dimensional micrometer stages are translated. These stages may not be very visible on this view graph owing to the fact that they are all black in color, but it's just a conventional XYZ stack. The same schematic is portrayed more clearly on the top right box. So we can vary pulse widths going all the way from sub 100 to 2 picosecond, sub 100 femtoseconds to 2 picoseconds. In some cases, we have used nanosecond pulses. That's from a different laser in a different lab with Professor Nilesh Vasa. Our stages are fairly precise, but can also be moved at fairly high speeds, over 200 meters per second. Their resolution is sub-micrometer and they're very repeatable. So in principle, one can process even a 6-inch silicon wafer, which one can consider to be a sort of industry standard. So high speed, high throughput, and hopefully I'll convince you that high precision is possible. Single step processes, owing to the way in which these pulses interact, is also something nice, or few step or few pulse processes, and we can more or less eliminate precast layers and therefore the need for post processing. This is a master's student, Mano, who is soon to graduate, and I will showcase some of his work. He is laying his sample into the micro machining end station. So what did Mano do? This is the first short story of this presentation. So Mano was one of the first students. He, along with Anubhav Sahu and other students, essentially took up the work on micro machining. Anubhav Sahu himself studied more the physics of the laser matter interaction process and some nanoparticles, which he synthesized using these pulses, and also did time resolved spectroscopy. But Mano's work, he essentially wanted to get the best working conditions and best features that are possible. So he drew grooves using the ablation of femtosecond laser pulses. You can see that a pair of grooves is written using this laser as a scribe. So there is a pair here, and these two grooves are coming close, and he wanted to try and optimize these grooves and bring them as close to each other as possible and determine a sort of pitch for these grooves. And he determined that we can space the two edges as close as about 2.5 microns together without destroying the integrity of the grooves and maintaining substantially good linearity among this. So this would, as one can imagine, be relevant for grating-like structures and writing more fluid channels and writing perhaps even waveguides for applications, right? So this was first proof of principle work. It was a few years ago, and we were really excited to see that we are able to do this. This also talks about the excellent quality of the translation stages we have. But then one of the first pieces of research, which was fairly successful, and Mano came up with this looking into literature, is to enhance the smoothness of these grooves, which is to say that reduce the roughness in as few a number of passes as possible in ablating material. So he took the most common material that one would want to do, one of the most common, which is silicon wafers, and under identical conditions, he ablated the silicon wafer in air, that's ambient conditions. He immersed the silicon wafer in propanol, in isopropanol, a very common solvent, then in methanol and in ethanol, and under identical laser scribing conditions, scribe these grooves by ablating the material and then examine them under a non-contact optical profiler. Seeing is believing, and the proof of the pudding is right here, in that we get very smooth profiles when we immerse these samples under a suitable solvent. Well, that is one of the alcohols. And in fact, we found that there are small differences between the different alcohols, and methanol somehow seems to perform the best. In one sense, this sort of rugged, the ridge structure with this very ill-defined surface is formed in air because of the fact that even in the femtosecond machining process, there is some debris, and unless we have a nice way to remove the debris as the process is happening, it's not going to give us the best results. And the liquid sets up a convection, and that convection takes away the debris efficiently, and also seems to regulate the thermal balance in the process well. It's not something we completely understand. We are actually taking to some modeling of the process using COMSOL, which is still work we are going through, and hopefully we'll have some results to report about that. Now, one of the important cornerstones of Mano's work is that he also took very unusual materials which have probably not been used to process with femtosecond pulses, such as cobalt chromium alloys and cobalt iron boron alloys, which are really hard materials, medically important materials like cobalt chromium, which are used to make stents, and PMMA on the other side, which are used to make intraocular lenses. So can we actually cut intraocular lenses out with femtosecond pulses, or maybe post-process them by smoothing them with femtosecond pulses? This was something we were very keen on studying. Apart from common silica, we also looked at films, cobalt, iron boron, and BLIG, which is a very important material for magnonics along with YIG. So under similar conditions, we essentially figured out the nature, the shape, and the width of grooves which which can be written across this spectrum of materials. And this is something Mano has reported in an IEEE conference. Well, now what do you do with all this in a lab? Essentially, one of the long-term goals of our collaboration and work groups is to exploit this for microfluidics, especially this is in context with work that we are carrying out with Professor Ashish Sen in mechanical engineering, in the mechanical engineering department. So we did simple proof of the principle experiments, and also to convince ourselves that we can do this well enough. So we wrote structures on biological slides, typically what is used in a setting like that, and we measured the flow rates as a function of different channel widths, and in this sort of scenario. So okay, I'm not able to really play this video in the current format, but maybe I can just come out from this and play it. Okay, it's not really working out, so let's not bother about it. But what we did was to color water, distilled water, with methylene blue, and then just make it flow through different channels of different widths, and you can see that there is a nice capillary flow through these channels, and we hope to exploit this in the near future. Now, in as much as we can make fluids flow, we can also look at the wettability of these surfaces before and after interacting with laser. There is sufficient evidence to believe that we can tune laser conditions in order to texture a surface and make it either hydrophobic or hydrophilic, and this is done, of course, using contact angle measurements. So in this case, which was just a one-off study, so basically we measured the contact angle after ablation, and we found that it is becoming more hydrophilic for the conditions that we have worked in. But for contact angles that are greater than 90 degrees, where the droplet becomes even more convex at the contact point, hydrophobicity starts to grow, and one even has superhydrophobicity. Indeed, other groups have shown that just by femtosecond laser processing of silicon, one can even induce superhydrophobicity. Our goal is to hopefully also control this on various different important surfaces, including polymers, so that we can make flat fluidic devices in the future. Okay, so now, Mano, of course, had a series of successes in terms of using these techniques. Now, in the second part of this talk, I would like to actually showcase our interaction with industry and real world through the work that Dr. Errol Maran, who is now a faculty at the MEPCO Schlenk Engineering College down south in Madurai, carried out as a part of his PhD here. In part in our lab, which is the femtosecond pulse work and nanosecond work with his two PhD advisors, Professor Nilesh Vasa and Professor Vijay Raghavan. So the idea here is to enhance the tribological properties of as obtained commercial tribological, you can say, devices, so that we can take these industrial components, process them, and give them back to industry, and it should be real world here, and use it for real world applications. So in such a scenario, one needs to carefully define the goals, both short term and long term, as to what we would like to achieve in terms of enhancing the tribology of these devices. So our goal is to try and develop processes which will enhance the tribological properties of a series of devices such as piston rings, cylinder liners, even drilling bits, which we heard about in Professor Ghosh's talk, and other abrasive surfaces, or non-abrasive, that's tribological surfaces, and implement this at both high throughput and high precision. Take advantage of ultra short pulse based surface texturing techniques, standardize and validate these processes for important materials and alloys such as steel itself, which is for automobile and aerospace alloys, important titanium alloys, which are important for aerospace applications, as well as medically important alloy materials such as titanium, cobalt, chrome, and nitinol. Now, there is also sufficient reason to work with non-metallic materials, which are polymers, especially high molecular weight polymers and ceramics. This also has tremendous application. In one sense, this is also motivated by the fact that tribology as an industry is rapidly growing in one sense, and one needs to reduce the cost, increase the throughput, and add value to end users, which would be automotive, aerospace, and medical device industries. This is the broad goal of this long-term effort, and I hope to convince you that we have made reasonable progress going towards this through Errol Maren's work. Okay, so the research flow is as follows: use picosecond or nanosecond pulses, whichever are suitable, mostly picosecond or femtosecond pulses to do ultra fast pulse surface texturing. We call this the UPST process, and then do tribological characterization, testing, and validation according to currently accepted industry standards, and transfer this technology, process, or know-how back to industry. Of course, we prefer working with as-is components which are manufactured by manufacturers such as India Pistons, which is a leading piston manufacturer in India, right? So in terms of the tribological aspects, after we do our microstructuring with ultra short pulses or femtosecond pulses, we do imaging both with optical profilometry as well as scanning electron microscopy. We use tribometry and hardness testing using a reciprocating tribometer as well as Vickers hardness testing, and we also engage with our industry partner so that we can actually validate the component that we have worked with in the lab. And we have already had some successes in terms of publications of Dr. Errol Maren. Okay, so what exactly did we do? So we took piston rings as is from our industry partner, India Pistons. These were molychrome coated, and the coating itself is about 130 micrometers. So we need to be delicate about what we are doing over here. The experimental setup is quite simple. We fix the piston ring on a sample holder, which is suitably designed for that. And then we translate the sample while we rotate it in the Z direction, almost as if we are binding a rope around a cylinder. But then here we are essentially focusing laser pulses, either femtosecond or nanosecond. In this work, we essentially compared femtosecond pulse based texturing to nanosecond and did identical studies in order to figure out if there is any merit in using femtosecond pulses at all. Hopefully, at the end of this presentation, you will be convinced that indeed it is preferable to use femtosecond over nanosecond pulses for enhancing tribological properties of piston rings. So this is a schematic. The whole idea is to write these nice threads onto this piston ring and then use it along with the lubricant in the normal industry setting. One can easily understand why we are trying to do this, because these grooves tend to become reservoirs for liquid lubricants, and hence tribological performance, wear and tear would be reduced, and the life of these components would be significantly enhanced. Okay, so the way in which microgrooves are formed, essentially using these laser pulses, is nearly identical. But just to recap what we are doing, we move the sample at a certain velocity. In both the nanosecond and femtosecond case, the target velocity was kept identical. The nanosecond laser was fired at 10 hertz. It was 6 nanosecond pulses, albeit at a green wavelength, 532 nanometers. In the femtosecond case, we used titanium sapphire laser pulses, but these fired at 1 kilohertz and pulse width was about 100 femtoseconds. And we scanned the stage at similar speeds. Okay, so essentially the grooves are formed because the laser pulses are partly overlapping, and we check this, of course, with optical microscopy, and these grooves tend to get formed, and we varied pulse energies in all cases. It is not that at all times the laser power was 5 watts, it was the maximum power, but the per pulse laser pulse energies that we used in the nanosecond and femtosecond cases were varied to be so. These pulse energies were chosen so that we get similar size of grooves or dimples on the surface of these piston rings. So now the rest of this presentation is going to detail out what we observed and hopefully convince you that one set of pulses, one may be a bit more expensive than the other, is still better suited for this application. So as good scientists, we study all the set of parameters that are possible to be varied in our experiment. So we varied the per pulse energy of these laser pulses, and this is in both cases, and also varied the number of passes we use for making these grooves. So what we then observed is that channels of different widths and depths are formed. So this is important because we would like to have as good a repeatability as possible in making these grooves, so that if for the same set of industrial batch of grooves, we'll be able to make a predetermined set of channels with a given width and depth. One should note here that femtosecond pulses were used at a central wavelength in the near infrared of 800 nanometers, whereas for the nanosecond pulses, this was at 532. The absorption coefficient of chromium is a bit different. It's about 50% different, but the mechanism of interaction is significantly different. In the case of femtosecond pulses, it's multi-photon absorption and ionization, whereas nanosecond pulses is more a heat dominated process. So this holds only so much importance in one sense. Okay, so the surface morphology of the channels that we made, grooves which we made, is very evident in this optical profilometry images. We can clearly see here that there is a bit of a recast bump on the sides of the nanosecond laser formed grooves, whereas in the case of femtosecond laser formed grooves, this is fairly flat, and this is kind of an evidence that indeed the grooves are much less collaterally damaged, or almost none, when we use femtosecond laser pulses. And if one did surface roughness measurements, as we showcase in this left panel here, the top row is nanosecond pulses, the bottom row is femtosecond pulses. You can see that the roughness within the grooves is also far smaller, almost a factor of 10, you can say, smaller in the case of femtosecond pulses as compared to nanosecond pulses. So of course, we would expect that these would be tribologically more preferable. And is that so? So yes, we first wanted to also test the hardness of the regions where we use laser pulses and see if there is some kind of hardening that's taking place because of melting and reforming and so on and so forth. So indeed, it was in Vickers hardness test measurements, we essentially figured that the percentage increase in hardness is 3 times in the case of nanosecond pulses as femtosecond pulses on an average. So this also tells us that okay, the femtosecond pulses are not so damaging, although they do the extrusion of materials very well. Now, but really, what we care about is tribological properties. So we did a reciprocating motor. We use a reciprocating motor to measure the tribological properties at various different loads, all the way from 10 to 130 Newton. We used the same oil in both cases for nanosecond as well as femtosecond laser pulse grooved or microstructured samples, and we studied the tribological properties. That's the work of Maran. And here is a very typical result which we found. Indeed, we found that for groove spacings of about 170 micrometers, the wear volume on the liner of these pistons is significantly smaller in the case of femtosecond pulses. It actually, nanosecond pulses don't perform too bad. Nonetheless, as compared to the non-textured material, the textured material performs way better. So, but then the wear reduction is actually much better in the case of femtosecond pulses. So one can sort of conclude based on these that it could well be preferable to, if especially if one is going to establish maybe a new system or a new industrial line, to use femtosecond pulses, which are becoming more and more robust. The laser systems are becoming more robust, and their cost is also reducing. It may be better to choose a femtosecond laser because not only is the friction reduction better in the case of femtosecond laser pulses, wear reduction is better, but also residual stresses on these materials are much more reduced in the case of femtosecond laser interaction. So this essentially is sort of interim summary of Maran's work, and with I will conclude this little test case by also presenting the details, a few details of the effect of lubricant temperature that on these grooves, on femtosecond textured versus femtosecond textured grooves. We used lubricants of 3 different temperatures, 50, 20, and 180 C, and different sliding speeds, 600 RPM all the way to 900 RPM under a normal load of 130 newtons. The goal of this study was to look at the effect of the these tribological parameters as a function of the density of the patterns on these samples, which will become very clear in this view graph. On the top left quadrant of the image of this slide, you see going from A, B, C to F, increasing areal densities of dimpled patterns on this test piece, and we performed essentially measured the coefficient of friction over here at different lubricant temperatures, going from 50 to 180 C at various different speeds. And indeed, in all these cases, we find that the higher the groove density, the better the tribological performance, as one would expect, and that these are not really critically dependent upon the lubricant temperature. We wouldn't really want them to be temperature dependent on lubricant temperature very strongly. So indeed, the performance of these femtosecond textured piston rings seems to be increasingly more and more convincing in terms of being applied to the real world and to industry. Okay, of course, that was about the study on the coefficient of friction. This is just one more representation of the same data in a different form. As compared to non-textured samples, the textured samples indeed performed better. Therefore, we sort of rest the case that this kind of texturing with very low thermal burden and debris is indeed a very nice idea. And here we also measured using non-contact optical profilometry, got a direct measure of the roughness of the surfaces, especially the used surfaces after the test. We measured their roughness, their wear and tear, and indeed it's very clear that both the dimpled surface and also the liner, which I'm showcasing over here, were indeed much better with higher groove densities when we used femtosecond laser pulses to texture them. Okay, now the wear volume of the liner was also measured, but in the interest of time, perhaps I should not elaborate the details too much. We could maybe discuss this in our question answer sessions. But then hopefully I have made a strong case over here to convince you that playing with pulses and using pulse lasers is a future direction for these studies. And we indeed would like to not just stop at academic or research labs. We would like to translate this to industry. As I said, we are working with our industry partners, India Piston Limited, and now more recently with QME, which is a Carborundum International, and Mahindra and Ashok Leyland, which are automotive um, companies, prominent automotive manufacturers in India, especially through the good offices of Professor Arunachalam, who has in fact himself also incubated a company that involves diamond membranes and devices thereof. But we will certainly continue our studies on piston rings and collaborate with also Indian Oil, which are lubricant manufacturers, apart from being petroleum vendors, to take this forward and interact closely with industry, which is really the goal of this research. And hopefully we will be able to meet the deliverables that our partners and funding agencies want, which is excellent micro texturing with a lot of control and precision, meeting global standards and keeping to important specs in terms of feature sizes, reducing friction and enhancing mean time between failures, benchmark them, keep them cost effective, keep devices indigenous, make in India, and at Indian costs, hopefully, which should be a tenth at least or more reduced in terms of indigenous versus imported costs ratio. If we do this, not only will we add to the technology and economy on the Indian firmament, but also what is becoming increasingly important is global energy consumption, especially in the automotive sector. This will have an impact on reducing fuel consumption, whether it is oil or even batteries. It really helps us to make our devices and even automobiles more efficient. So, but then the physicist in me wants to restate and reaffirm the following fact, that indeed at the heart of all this is some very exciting physics which happens on femtosecond or picosecond time scales. Some of this was recognized and heralded by the first Nobel Prize given for femtosecond light matter interaction in 1999 to Ahmed Zewail. And physicists have toiled before and after this and continue to toil now to understand better how these very nice pulses interact with matter. And this was once again recognized, and the importance of this science was recognized, especially from the perspective of LASIK surgery, and a Nobel Prize in more recently 2018 was given to the father of modern amplified femtosecond lasers. You can say the father and mother, but this is actually PhD advisor and PhD student Gerard Moreau and Donna Strickland. So I hope this journey convinces us that not only, as Feynman said, is there plenty of room at the bottom, but I guess we also have plenty of time at the bottom. So with that, I would like to thank you for your attention and the organizers for this opportunity, and alongside wish everyone here and whoever may listen to this talk even later a healthy, happy and successful year, all of which are important in the present context. With that, I will stop here and hand it back to Professor Kong.
So thank you very much, Professor Krishna Sanji. Your presentation is wonderful again. So I would like all of the audience to join me to thank both speakers for their wonderful speeches. So actually, we have a couple of questions for you. The first one, I will send you answer most of the questions already about the person would like to know more about it. You might quickly answer the question to say what is femtosecond pulse, laser pulse, and its applications.
Yes, so as I said, one of the important applications of femtosecond pulses is to do micro structuring, micro machining, and even nanoscale welding of materials. But then if one reads the citation of the Nobel Committee for the prize that was given in 2018 to to the inventors of the femtosecond laser amplifier, specifically chirp pulse amplification technique, which underlies all these relatively high energy pulses uh, that we see in modern lasers. They cited that these are poised to revolutionize surgical light laser-based surgical tools. Well, the importance of that is probably in the human context very important. Now, think of while a surgeon performs a surgery, very precise cuts are needed, right? So that's really the reason why laser pulses are ideal tools, but these are light tools, as actually the Nobel Committee observed. The other Nobel laureate was Arthur Ashkin for optical tweezers. So these are all tools made of light. So this light tool is really very good because it makes very, very precise cuts. In our case, we are scribing, but that's also, loosely speaking, a cut. So which laser makes the most precise cuts? Is this a continuous wave laser, a 405 nanometer diode based laser, which is used for metal engraving everywhere? You can buy it on Amazon India, though it's not safe. So please don't do that without much thought. Or is it nanosecond, or is it femtosecond? Indeed, it's these femtosecond laser pulses which work best. In fact, this was discovered by accident or serendipity, apparently in Professor Muru's lab, and this is not a good example for graduate students. One of the students removed the laser safety goggles and looked where he or she should not have looked, and then got a bit of laser in the eye. And of course, immediately one goes to an ophthalmologist for an examination. He went to his regular ophthalmologist and feared that he would be blinded. Indeed, these pulses can very easily blind us, but luckily he probably got an optimal dose of radiation. So his ophthalmologist apparently knew that he had some other maybe structure or whatever in his eye, and the laser made a cut and it seemed to have improved his vision or something like that. That's the anecdote. So, so then, of course, the clever PhD advisor realized that these would be very good for surgery. Of course, this must be very, very controlled when we use it for surgery. In fact, a whole lot of modeling is really important before we can take this in the eye, and one should never ever do this at home or in the lab. But then in a controlled way, one can indeed use these pulses. But just to tell you, earlier LASIK surgery, or the most popular tool, is actually excimer lasers in the ultraviolet, which of course is well known to the experts. So now femtosecond pulses can possibly add a new dimension to that. But of course, the costs are increased. Yeah. So
we can't agree more. So another question was, can this ultra short laser pulse be used on glass for creating simple textures, for creating micro lenses? I said that's some similar to what you said, that could be used for eye operations.
Yeah, indeed. So indeed, Professor Kong, you made a very pertinent observation yourself in the process of asking the question. So yes, this is not something I highlighted, although I work in photonics. We have not yet started doing creating refractive index modifications, but it is very popular to write waveguides using these femtosecond pulses, and one can also write these waveguides using femtosecond pulses well beneath the surface of interaction. So yeah, for example, this cartoon here, which actually was shared to me by Professor Uwe Mogner from the University of Hanover, they do some very wonderful work, but I cannot showcase his work as ours. Maybe I should have asked Uwe and shown a couple of view graphs. These subsurface lines, the yellow line being written is beneath the surface, and it creates a refractive index modification. So one can, in an optical fiber, light is guided by the fact that the core of the fiber has a refractive index which is smaller than the cladding, and so this very high school phenomenon of total internal reflection tends to guide light rays. And for Indian students, you may be delighted to know that the father of this technology was an Indian American, N.S. Kapani, who actually sadly passed away recently, but there is a nice biography of him in Nature. But this phenomenon is very nice, and one can indeed use this to write waveguides. But what I did not describe was other types of waveguides called type 2, where you can use other tricks to do waveguide formation, indeed with femtosecond pulses, to modify refractive indices in situ. Even the more complex photonic structures have been demonstrated. So you can guide light, but the question was about micro lenses. Yes, indeed, when you can modify refractive index in a very precise way, you can create lenses. People have done that. In fact, we would also like to make some of these so-called solid immersion optics using femtosecond laser pulses. But there even maybe a set of hybrid approaches, nanosecond or excimer, and then femtosecond may also work better. Who knows? But certainly with these techniques, it's good. But even though this was not posed, maybe I should also put this forward. There are other techniques like focused ion beams which can do this maybe at higher precision. However, just the fact that we can actually do most of these processes in air, we don't need to really create ion beams, makes this process effectively more cost effective, although at slightly larger values of resolution of feature sizes. But for micro scale engineering over a large area, these pulses are ideally suited. Yes,
Absolutely, I totally agree. So actually, I really appreciate this opportunity to know both of you. And if you announce, particularly once the pandemic is done, it's gone, I would love to make a trip to India and to IIT Madras to meet you and other colleagues to seek further collaborations. So thank you very much for your wonderful presentation. So probably now we will, I would like to invite other panelists to join me to also say a few things. First, I would like to invite Professor Samuel, because this is a wonderful initiative. You form a Center of Excellence and to use the very, very advanced technology like laser technology. And also you have some vision to help manufacturing industry in India, probably worldwide. So I would like to say certainly the sky is the only limit for us to use the laser technology. Would you like to see a few words on the initiative and also the perspective of the center?
Yeah, thank you, Professor Ling Sukong, for accepting our invitation and moderating this program. So we also would like to thank Professor Amitav Ghosh and Professor Shivaram Krishnan for giving the insight into the practical aspects and the fundamental aspects. So it was really nice indeed. So it has been very fruitful. And also, Professor Ling Sukong, we invite you to visit our Center of Excellence. So we have the provision to come. So whenever the borders are open, you are welcome to visit us. And we'd also like to acknowledge the presence of Dr. Ravi Bate, scientist from ARCI Hyderabad. So who has also been working in this area of texturing of the piston rings. Professor Dr. Ravi Bate would like to add anything?
In fact, it's a pleasure to see Professor Ravi Bate here. Good evening, Professor Bate. I'm sure you'll have a lot more to say about texturing as well. Please go ahead.
Dr. Ravi Bate, your mic. Okay.
Hi, Professor. Very fast. Would you be able to unmute you as yourself and say something first?
Okay, I think if anything is further is there, it should be fine. We'll move ahead. Yeah, Professor Ling Sukong, I think we can conclude now. So it is 7 o'clock and it has been like 12:30 in Australia now. So
okay, thank you very much. And yeah, I also like to say a few words to Rachel as well. Thank you for coordinating this webinar, and good night to you, and good morning to me. Actually, it's early morning in Australia, and I would like to finally thank Professor Gush and Professor Krishnan for delivering such wonderful two presentations. Thank you very much.
Thank you. Thanks a lot, Professor Kong, for joining us today. It's like you said, it's a good morning to you. I hope you do have a great day, and thanks a lot. It was wonderful to hear you and everyone on the panel speak. Special thanks to Professor Ghosh and Professor Krishnan, and thanks a lot, Professor Samuel. We couldn't hear Professor Bate, but yeah, hopefully we can have another session sometime soon again. And thanks to everybody who joined. Thanks a lot.
Okay, bye-bye.
Thank you so much, Richu, Ms.
Good
Richu, for
night.
this effort. Thank you, Professor Kong. We really look forward to your visit here and
Okay,
also
thank you.
possible
Me
joint
too.
efforts in the future. Yes. Thank you so
Okay.
much.
Okay,
Bye-bye.
thank you all.
Bye-bye.
Yeah, we thank the Office of Global Engineering for coordinating and arranging this. So Ms. Richu and Ms. Lisa. So thank you all for the whole team. We have been organizing this very well. Thank you all the participants for staying with us. Thank you everyone. Take
Thank
care.
you.
Bye-bye.
Thank you.
Yeah.
Thanks, everyone.
Thank
Bye.
you, Bruce.
Good night, and
Okay. Thank you all.